Friends, we will today start a new technology, which is almost a sister of catalytic reforming, in the sense that both are actually supplementary and complementary to each other in many ways. And we will learn why they are so. And we are going to talk about, and actually, this is not a very this is not a very involved technology. So we shall finish it in today in the today's session itself. And this is actually C5C6 isomerization. So in this module, what you will learn is the chemistry and the reaction mechanisms, what happen there, the catalyst and the catalyst poisons, the thermodynamics of isomerization, the operating variables, as well as the commercial flow sheets in the way we practice this technology. Before I begin, I must tell you that it's something that has been implemented in almost all refineries in India, particularly to meet Bharat Stage 6 requirements of gasoline specification. In other words, we have already gone through in great detail the whole specification of gasoline. And you would recall that we have four major limits, rather five major limits. Number one, of course, is the sulfur limit, which is less than 10 ppm. So the isomerate like reformate is very low in sulfur, almost 1 ppm in sulfur. The second most important thing is the benzene content, which is less than 1%. So isomerate actually helps to meet that specification because it has zero benzene. The third specification, if you recall, was the total aromatics, and that also isomerate, helps us to meet because the total limit is 35% aromatics. Reformate actually brings a huge amount of aromatics, so isomerate dilutes that in terms of meeting the overall. And the fourth is, of course, the olefin content. So, like if you mix FCC gasoline, the olefin content goes up, and this doesn't have any olefins at all. So it's a very important technology which is required to meet the Bharat Stage 6 requirement. And as I promised to you earlier, before I begin any new technology, it's very, very important to understand where it belongs to in the whole scheme of things. So if you recall the whole naphtha, which comes out of the atmospheric distillation column, it goes into a column called naphtha stabilizer, where actually we recover LPG from naphtha. And then that full range naphtha is then distilled to separate out what is called as a light naphtha and the heavy naphtha. The light naphtha is everything which boils all the way from the initial boiling point, which is C5, right up to 90-95 degrees. We try to bring in as much benzene precursors as possible into the light naphtha, because if they remain in the heavy naphtha, they will actually tend to increase the benzene in the reformate, and that would actually not help us to meet the benzene spec on the gasoline pool. So this we have already discussed when we discussed catalytic reforming. So the initial boiling point of the heavy naphtha is adjusted in such a way that we don't actually have any of those benzene precursors going into the catalytic. And what I mean by benzene precursors, these are like hexane or methyl cyclopentane or cyclohexane, because they will immediately go to convert to benzene in the reformer. So we try to bring all of that up into the light naphtha. And as usual, the light naphtha is hydrotreated. Many a times what we do is that we actually hydrotreat the full range naphtha, and then we fractionate it to the light and the heavy. And then the light naphtha then goes into the isomerization unit where you get the isomerate, which goes into the blending pool. And as I mentioned before, it actually helps to meet the overall gasoline specification, because to a large extent, it actually supplements and complements the reformate quality. Now, if you talk about the feed to this unit, this is like light reformate, light naphtha. And when I say light naphtha, it essentially consists of C5 and C6, no C7. Okay. As you can see, the C7 content is limited to not more than 1%. Please remember this. The C7 content is not allowed to go up beyond 1%. And obviously, we are trying to bring in benzene and the benzene precursor. So you can see that methyl cyclopentane is about 5%, cyclohexane is 1.5%, and we have benzene as well. But essentially, what this thing contains is basically paraffins and to a small quantity of isoparaffins. So what happens in this unit is that all the normal paraffins get converted to isoparaffins. This is essentially this unit does. Okay, the C5 C6 isomerization unit. The main purpose of this unit is to actually convert the C5 and the C6 normal paraffins to isoparaffins. And the reason is that actually, as at this table, you must have actually got sick and tired seeing it again and again. But it's very important to understand why we need to isomerize because, as you can see, all the normal paraffins have a low octane, while actually the isomers, like for example, normal pentane is 61. But if you look at the isopentane, like the dimethyl 2,2-butane, this is of course C6. So the octane number is high. I mean, this is octane and this is RON is the research octane number, and the MON is the motor octane number, which is actually something which is required if you're actually running on a highway at 100, kilometers an hour. So at that time, this octane is extremely important. So you can see the normal heptane is zero. We don't actually have much of C7 anyway in the feed. But there's one more thing which I would like to point out. When we come to C6, that is normal hexane, its octane number is only 25. There are two types of isomers that you can produce when you isomerize normal hexane. One is a single branched isomer like 2-methylpentane or 3-methylpentane. This is an isomer. This is an isomer of normal hexane. But its octane number is still relatively low, higher than normal hexane, but still relatively low. But if you do double branching, like 2,2-dimethylpentane or 2,3-dimethylpentane or 2,4-dimethylpentane, you can see that the octane number goes up. In fact, the 2,2-dimethylpentane has the highest octane number. And so, in fact, when you isomerize pentane, you get, you get, where is that gone? Yeah, dimethyl butane, and that octane number is high. So basically, the pentane is isomerized to isopentane right here. So I was looking for that. Yeah, the isopentane is 92.3. While this is only one isomer that you can produce out of normal pentane, so the carbon positions can change. But you can see there is an increase in 30 octane here. So this is why actually we try to isomerize the normal paraffins to isoparaffins. But nonetheless, if you look at the feed, it also contains any natural feed, any straight run feed would contain a mixture of normal paraffins and isoparaffins. The relative quantity of isoparaffins is low. So when you go through the unit, it goes up. So this is shown in this table. So where you can see that if you look at isopentane, in the feed it is 21%, in the product it goes up to 35%. This is the feed to the isomerization unit. In our refinery, we actually don't call it as a complete isomerization unit. We just call it as an isom unit. We just use the first four letters. That is the ISOM unit. So I'll use this word because I'm more conversant and more comfortable in using that word. So basically, if you look at an ISOM unit, the feed going in is here, the product coming out is here, which is called the isomerate. And you can see that the isopentane goes up, the normal pentane goes down because that gets converted to isopentane. If you look at the C6 part, nothing happens to cyclopentane, and we'll talk about these naphthenes later on further, like cyclohexane, cyclopentane, etc. What roles do they play? But when you can talk about hexane, you can see normal hexane going from 18.6 to 5.1. And a lot of that gets converted to both single branched isomers like 2-methylpentane, 3-methylpentane, here there is a reduction because this 3-methyl pentane got converted to double branched C6 isomer. So you can see initially there was nothing, but in the product it is high. So you actually get roughly about 13 to 15 increase in octane. Nothing great to actually write home about. But why we do it in the industry? I mean, why are we fishing around for this 13 increase in octane and investing money in this technology? As I said before, it's a huge diluent. It has no sulfur, it has no benzene, it has no olefins. And so actually it acts as a big diluent while maintaining a reasonably high octane number. So let us talk about the chemistry and catalysis of isomerization. If you recall, I had mentioned that there is some benzene in the feed, right? That's how we cut the naphtha in the light and heavy naphtha. So we need to get rid of this benzene. So the first reaction that we try to do in isomerization is to actually hydrogenate benzene. So benzene gets hydrogenated to cyclohexane. So that's how we get rid of benzene in this. And of course, whenever you have a hydrogenation reaction, by definition, by thermodynamics, it is exothermic reaction. And this is exactly the reverse what happens in catalytic reforming. So this reaction is exothermic and it occurs in the hydrogenation reactor. So the idea is to actually reduce the benzene down to less than 0.18%. So this is the first reaction that is done. The other reactions are, of course, the isomerization reactions, which involves nothing but the rearrangement of the structure of a molecule to its more branch structure. So, for example, if you take this normal pentane, that is CH3, CH2, 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 CH3, that is isomerized to a branch structure like that, which is called isopentane. There is also a possibility of making a neopentane that is just one carbon and four carbon, four CH3s around it. But that is thermodynamically unstable compound. So this is practically never found. So when you talk about C5, normal pentane in the feed, the only product that you get is the isopentane, which actually improves the octane almost by 30, from 60 to 90. If you look at the C6 part, these are the only two, C5 and the C6, these are the only two carbon numbers which are present in the feed. So if you look at the hexane, which has got a very low octane, that actually isomerizes to 3-methyl pentane, which can further get isomerized to 2-methyl pentane, and then to the double branching, that is the 2,3-dimethyl butane and 2,2-dimethyl butane. You would have noticed the double arrows here, both in the pentane and the hexane. So it's very important to remember that it's an equilibrium control reaction. Okay. And all these isomerization reactions are mildly exothermic, around 20 to 25 kilocalories per mole. And that is the reason why, again, as per Le Chatelier's principle, we would like to actually carry out this reaction at a lower temperature so that we shift the equilibrium towards the right. Okay. And that's the reason why you would have seen from this table that not the entire hexane got converted, not the entire pentane got converted. You still have some normal pentane because actually some of the isopentane would also actually form normal pentane because it's an equilibrium control reaction. But the idea is that we choose the catalyst and the operating conditions in such a way that we actually favor isopentane formation in case of C5 component present in the feed, and to make double branched isomers, that is either 2,2-dimethylbutane or 2,3-dimethylbutane, so that we actually have a higher octane. There are two undesirable reactions as well in this process. One, of course, is the coke deposit on the catalyst, and I'll come back to that later when we talk about the types of catalyst used in this technology. But the other side reaction is the hydrocracking reaction. And this hydrocracking reaction is actually promoted because of the acidic sites on the catalyst, where actually there is this reaction is carried out under hydrogen-rich atmosphere. The reason why we actually have hydrogen along with the feed is to actually suppress coking. And because of that, hydrogen hydrocracking takes place. And but of course, it's it's the metallic as well as the support which actually takes part in that hydrocracking reaction, and so we make some light ends like LPG components. Also, if you remember, we were cutting the naphtha in such a way that we get all the benzene precursors into the light naphtha. And so basically, cyclopentane, methyl cyclopentane, cyclohexane, they are present in light naphtha. They are not actually, very desirable, but they also undergo the reaction. Actually, they get hydrogenated to make normal pentane. So there's a ring opening and hydrogenation to make normal pentane, normal hexane, and so on and so forth. And then, of course, the normal pentane, normal hexane, they get into the isomerization process to get converted to the corresponding isomers. These naphthenic or cyclic compounds present in the feed, they actually do inhibit the isomerization reactions because they get absorbed on the catalyst surface and reduce the active sites. So actually, too much quantity of naphthenes in the feed is not a good news actually. To some extent it is okay because it will get hydrogenated to make these paraffins, but large quantities actually inhibits further reaction because they deactivate the catalyst by actually getting absorbed on the surface. And of course, you do get hydrogen consumption, so you have to actually put more hydrogen in order to convert the. Of course, you get higher yields though, but it leads to hydrogen consumption, and all these hydrogenation reactions that you see here, that is both the hydrocracking reactions as well as these hydrogenation reactions, are exothermic. As I told you many lectures ago, in our industry, whenever you actually put hydrogen into the system, it's an exothermic reaction. And whenever you take out hydrogen, like in catalytic reforming, it's an endothermic reaction. So these are exothermic reactions, and it leads to increase in temperature, which actually inhibits isomerization because of thermodynamics. So we have to actually make a special effort to carry away this heat as quickly as it's generated. So we have actually almost touched upon thermodynamics so far, and thermodynamics actually plays a very key role in isomerization because it also actually governs the kind of catalyst that you should be using. Remember, I told you that this particular reaction is mildly exothermic. And so basically, what we try to, and all the reactions are equilibrium controlled. So temperature and pressure. So the equilibrium state is, as you know, is governed by temperature and pressure. If you look at the pressure part, and I'll come back to that later, let's look at the temperature. If you look at the temperature, if you try to go up on temperature, and this you can do very easily, using some of these commercial simulators like HYSYS, Aspen, etc., where if you try to simulate this reaction of normal pentane going to isopentane and study the effect of temperature, you will see that the isopentane to normal pentane ratio does drop, okay, as you go up on temperature. And so it's very, so generally we carry out the isomerization reactions in this kind of a temperature range below 160. And for C6 hydrocarbons, which is basically normal hexane, if you plot the double branched, isomer of hexane, which is 2,2-dimethylbutane, versus temperature, again, you see the same effect. So we have to actually try to use a catalyst which can actually operate at a lower temperature. So the key here is to be able to find out that catalyst which can support good enough rate of reaction even at a lower temperature. Because as you know, the rate of reaction is governed very strongly by Arrhenius equation. You must have studied it in your undergraduate classes. So rate of reaction is the forward rate constant is equal to K0 into E to the power minus E upon RT, where E is the activation energy. And we talked about it during catalytic reforming as well. So temperature has an impact on the rate of reaction. So we have to actually find a catalyst which is which supports even reasonably good rate of reaction at a lower temperature. And if you look at, in the whole thing in combination, percent in mixture of C6 paraffins at equilibrium, you can very clearly see that if you really want significant quantities of 2,2-dimethyl benzene, we really need to go at a lower temperature. Okay. So this is one important thing to remember, that optimum operation which corresponds to maximum isopentane and maximum double branched isohexane, that is 2,2-dimethylbutane. We need to actually react at a lower temperature. And this also actually helps us in a way because it actually reduces the hydrocracking reaction. So what we try to do here is that we try to do this reaction in a two reactor system in order to take advantage of both the worlds. One world is the reaction kinetics, the other world is the thermodynamics. So what we try to do, and this is something that you will find very often and very common in many of these technologies, as we will talk. Like for example, whenever there's a exothermic reaction, and the reaction is controlled. I mean, the forward reaction rate is actually, and it's an equilibrium control reaction. Then we like to go to a lower temperature because it's an exothermic reaction, but then the lower temperature reduces the rate of reaction. So generally, we do these reactions in a combination of two reactors. The first reactor we operate at a higher temperature to take advantage of a higher rate of reaction, that is using this is kinetics. And the second reactor we actually operate at a lower temperature in order to actually take advantage of thermodynamics. So this is what we do in the isomerization unit also. We use a combination of two reactors, the first one at a higher temperature and the second one at a lower temperature. Now that actually brings us to the discussion of what kind of catalyst is used here. You would have by now anticipated that we need a highly acidic catalyst here because this acid catalyst actually help you to promote isomerization. And there can be nothing better than gamma alumina, where actually the alumina is like in catalytic reforming, is enriched with chlorine. That means we replace the OH group in the alumina with chlorine. So we actually try to enhance the natural acidity of alumina by addition of chlorine. And like catalytic reforming, we also actually impregnate the alumina with platinum. And the reason why we actually need a dual functionality here is actually because of the need, and there are two types of catalysts. The function of this dual, I mean, the function of the platinum is different in both these catalysts. So we'll talk about the functionality of platinum in a few moments from now. But what it essentially does is that it helps us to keep the catalyst surface clean. In other words, since we are doing this reaction in the presence of hydrogen, it actually helps to clean up the coke deposit on the surface, because remember we are using a high acidity alumina. So high acid alumina will tend to actually crack the hydrocarbons, and because of which you have coke deposit on the catalyst. So this platinum helps us to actually keep the surface clean. And it is also required to maintain the catalyst activity because otherwise, this alumina support, basically the real main catalyst is the alumina, believe me. The main catalyst is the alumina, but we actually put platinum as a promoter in terms of a servant. It's like a servant trying to actually clean out the surface of the alumina catalyst whenever coke gets deposited. So it's more like a scavenging operation that platinum does here. And this is how we actually, we put quite a bit of chlorine, almost like 8 to 12% by weight chlorine. And so actually, this catalyst activity it's almost like aluminum chloride, if you might ask me to. It's almost essentially, it's no longer aluminum oxide or aluminum hydroxide. It's almost like aluminum chloride. So we are essentially trying to do a Friedel-Crafts reaction. If you still remember a lot of your undergraduate chemistry, you would have learned Friedel-Crafts reaction. And Friedel-Crafts reaction means we have to use aluminum chloride, which has got a pretty high acidity. Now this is one limit of chlorination, but here we have somewhere in between where we have got both the hydroxides as well as the chlorine. But like aluminum chloride hates water. I mean, if you add water into aluminum chloride, you'll get HCl formation, and you will lose chlorine from the surface. So similarly here, water is a big enemy here. This explains. I mean, if the feed contains moisture coming into the reactor, it will kill the catalyst. So that is why we have to actually make the feed bone dry. The dew point specification of something like -30 or -40 degrees Celsius are not uncommon in our industry, as far as isomerization reactions are concerned. So it will be huge investment actually in terms of drying the feed. There are three types of catalyst. I mean, if you look at all the isomerization catalysts which are used in the various refineries, not only in India but around the world, you will find that they generally belong to three buckets. The first, of course, is the zeolite type catalyst, which is great actually to have because this is not highly acidic, and therefore it is not that susceptible to moisture. It's pretty robust, and the great news is that you can regenerate the catalyst in situ like you do the catalytic reforming catalyst. It gives you reasonably good octane, but unfortunately, it has to operate at a higher temperature. And since it's pretty active at about 280, 290 degrees Celsius. So actually, at those temperatures, because of thermodynamics, your extent of conversion gets reduced. Generally, people would prefer to have a zeolite type catalyst, but because of the reduction in the yields of isomerate, that is the isomers, people actually go for what is called as a chlorinated alumina catalyst. This is, in other words, in our industry, it is called platinum on chlorinated alumina. And chlorinated alumina is something that you saw here. It is somewhere between aluminum oxide or aluminum hydroxide on one end and aluminum chloride on the other end. So it's somewhere in between, something like 8 to 12% chlorine. Okay, and this is, of course, one of the major workhorse of the industry today. If you look at all the units, in fact, in our own country, excepting one refinery in Bongengao, that is the Bongengao Refineries Limited. Bongengao Refineries it is called BGR, Bongengao Refinery, which has now become it has now become one of the refineries of Indian Oil. They have actually used platinum on morganite, which is actually the zeolite type catalyst. But other than that, right across Indian Oil, BPCL, HPCL, everywhere, there you have chlorinated platinum and chlorinated aluminum. In Reliance, we don't have any C5, C6 isomerization unit because essentially the light naphtha that we produce in Jamnagar is actually sent to Hazira, where we have a world scale naphtha cracker. So there actually we crack that naphtha, the light naphtha, to produce ethylene, propylene, butadiene, aromatics, and all kinds of chemicals and petrochemicals. So that actually gives you a much higher value rather than converting light naphtha to gasoline. And that might be the way actually things might happen in the future, where this particular technology may not find much use later on because if suppose we don't need gasoline, then why do isomerization anyway? But nonetheless, I think as long as we have got IC engines, we need gasoline. And so this particular catalyst, the platinum on chlorinated alumina, gives you fantastic octane. In fact, the octane that you get by this catalyst is almost 5 to 6 numbers higher than platinum on morganite. It is regenerable, but it is not. It cannot be regenerated within the reactor. You have to unload the catalyst and send it to the people who can regenerate, and they give you back. But it is highly sensitive to impurities, and one of the major impurities is moisture. The third is actually mixed metal oxide, like platinum on zirconia. It had its own day, but I think I don't see much use of platinum on zirconia anymore. And they are. This is how they stack up. Actually, if you look at these three catalysts, this is. Let me explain what the y and the x-axis are. On the y-axis, we have plotted the ratio of the double-branched isohexane, that is the 2,2-dimethylbutane upon the normal hexane in terms of percentage, because this is important. I mean, this is controlled by the temperature based on thermodynamics. So as you would imagine, if you go up on temperature, this ratio would come down, and this is shown by this graph. And these are the temperature ranges in which these three catalysts operate. So you can see that the blue bar is where actually you have platinum on chlorinated alumina. Okay. Si2 is nothing but the commercial name of the catalyst being marketed by one of the catalyst companies. So this is actually the range in which it operates, and that is the reason why the industry prefers this catalyst, because at a lower temperature it gives you pretty high amount of 2,2-dimethylbutane. On the other end of the scale, you got platinum on morganite, which I told you is pretty active in this temperature range, but it suffers with the lower isom production. Somewhere in between is actually the platinum on on sulfated zirconia, and as I told you that either people use the platinum on chlorinated alumina, or in some cases platinum on zeolite. This catalyst is no longer in use. Let us talk about the reaction mechanism, and this is for the first time. I'm trying to introduce a new word to you, what is called as carbocation, and you will actually learn more. In fact, I did not actually get into those types of great details in catalytic reforming in terms of actual reaction mechanism. But catalytic reforming also goes through a carbocation mechanism. And let me actually teach you what exactly this is. So whatever may be the type of catalyst, whether it is platinum on chlorinated alumina, or whether it is platinum on morganite, we do have the mechanism going through carbocation. Now, let us talk about chlorinated alumina. Both these catalysts have different mechanisms, by the way. Okay. So let us talk about chlorinated alumina. In chlorinated alumina, what happens is that since it's a very highly acidic catalyst, it has been established that the monofunctional acid mechanism is involved, and in this case, the carbocation is formed by removing the hydride ion from paraffin, as seen below. So here you can see that this is my normal paraffin right up here. So 1, 2, 3, 4, 5. So this is like normal pentane. and this actually gets on the acidic side of the catalyst, you get a hydride ion generated. So you actually make a what is called as a secondary carbocation. This is called as a carbocation because this there is actually a this is an ion with one hydrogen deficiency. That's why it is called carbocation. But this carbocation is highly unstable. This is called secondary carbocation because this particular ion, this particular group, CH group, has a plus on it, and you got two carbon links here. So this is called secondary. This is highly unstable thermodynamically. So it actually rearranges immediately to what is actually called as a tertiary carbocation, where actually the carbon on which you have which is ionic actually gets linked to three carbon side by side. This particular type of carbocation is thermodynamically more stable. And so this particular carbocation, which is called secondary carbocation, gets converted into a more stable tertiary carbocation. And what happens then is that this actually then so the formation of isoparaffin by hydride transfer between above carbocation, this actually combines on the acid catalyst surface with another molecule of normal paraffin. So here you got one molecule of normal paraffin reacting with this carbocation, and what you get now is actually the isoparaffin plus actually a secondary carbocation formed. And this chain reaction continues. So let me actually repeat what I have said, and that is that the normal pentane molecule, when it gets in touch with the highly acidic site of the catalyst, it gets actually ionized in terms of liberating a hydrogen ion and making a secondary carbocation, which by itself is highly unstable, and that gets converted into a tertiary carbocation given here. And this tertiary carbocation then actually reacts with another molecule of normal pentane to form an isopentane plus a secondary carbocation. And this secondary carbocation will get actually then converted to a tertiary carbocation. And this tertiary carbocation will then react with another normal pentane molecule to make another isopentane. But of course, these reactions are all reversible. Okay. And so this chain reaction continues as far as the platinum on chlorinated alumina is concerned. So you can see that in this particular catalyst, there is no role of platinum as such. All these reactions are happening because of the acidic sites on the alumina. And but actually the platinum is required because at that temperature, because of the high acidic sites, you do get cracking, not hydrocracking, but cracking of the hydrocarbons because of which carbon gets deposited on the catalyst, I mean the alumina, and the platinum actually takes action to remove that carbon using the hydrogen in the atmosphere. The second type of catalyst, which was actually at the end of the scale, that means on the higher temperature, which is active at a higher temperature range, which is platinum on morganite. Morganite is one form of zeolite which are less acidic. Okay, so as I told you earlier, we don't really need to invest on dryers. We actually essentially don't need any dryer in zeolite catalyst. So there's a one big saving on investment. And the reaction mechanism, what happens here is actually then the metal function becomes active, the platinum part. How it becomes active is that actually, let's say this is the normal pentane, it actually gets dehydrogenated to make olefin. There's exactly the same way as we saw in catalytic reforming. And so you get hydrogen liberated. And so initially the olefin comes from paraffin dehydrogenation and then the carbocation is formed. So this olefin then actually reacts with the acidic surface of the catalyst in order to create a carbocation, which is now a secondary carbocation, plus the acidic site is there. Now, this carbocation, since it is unstable as before, it gets converted to a tertiary carbocation, and this tertiary carbocation then on the acidic surface gives you actually the iso olefin, and this isoolefin then reacts with the hydrogen which is present in the atmosphere, because the double bond is pretty active. So it gets saturated to make your isopentane. So the reaction mechanism between the two are quite different. Here we don't need platinum as a hydrogen transfer agent. The actual ionization in terms of removing the hydride ion is done by the alumina. But in case of platinum or mornite, it goes through the olefinic route. You get the olefin, normal olefin formed first, which actually then gets that gets converted to a carbocation, and that carbocation then actually rearranges itself to a tertiary carbocation, and this tertiary carbocation then actually reacts with the acidic surface to actually liberate the H ion to make into that the acidic surface complete, and in turn becomes an olefin, an isoolefin, and this isoolefin gets hydrogenated to make. So actually, there are multiple steps involved, and that is why the rate of reactions are slow, and you need higher temperature to actually convert a paraffin to an isoparaffin. So based on this, I mean, these reaction mechanisms actually decide what kind of operating variables you need to have to operate this unit. And there are five primary process variables which have a direct impact on the isomerization reaction. Number one, of course, is the reactor temperature, which is the critical. I think you must have appreciated and understood by now. The second is the space velocity. Again, similar to catalytic reforming, if you actually have a higher velocity, you have less residence time. So, in other words, less reaction. Again, hydrogen to hydrocarbon ratio, but here the hydrogen to hydrocarbon ratio has a different connotation, not exactly the same like in catalytic reforming. Here, basically, hydrogen is kept in order to suppress coking. And very similar, of course, to catalytic reforming and the feed composition, which the operator doesn't have much control really. It all depends upon what crude you're processing. But more important is the chloride injection. So actually, it's very important to maintain a certain level of acidity on the catalyst if you really need to have a significant reaction. As far as the first variable is concerned, reactor temperature, which is really in the hands of the operator, similar definitions are here as well, because now you have a two reactor system. So weighted average inlet temperature, and of course there is not much temperature change across the reactor. It's mildly exothermic, but where you might commit at about 150 and leave at about 155, something like that. So reactor inlet temperature controls the degree of isomerization. Higher temperatures, of course, enhances catalyst activity, but it decreases the degree of isomerization because because of thermodynamics. And higher temperature also increases hydrocracking. So it's always good to maintain at a lower temperature. So as I said before, we actually try to take advantage of both the worlds by actually starting off at a higher temperature and then ending up at a lower temperature. And so we use two reactor system. The first reactor operates at a higher temperature. Most of the isomerization reactions actually occur in this. In fact, what is important is the ring opening of the cyclohexane, which needs a higher temperature. So the cyclohexane and the cyclopentane gets converted to hexane as well as pentane in this reaction. So there is significant hydrogen consumption. And since the temperatures are high, we would actually like to we can absorb some level of exothermicity here. It helps all in both ways. But once we have got rid of all the cycloparaffins and at least got some significant rate of conversion, then we actually move on to the second reactor. That means we put a cooler to cool the product coming out of the first reactor, and then enter into the second reactor at a lower temperature to take advantage of thermodynamics. And the second variable is the hydrogen to hydrocarbon ratio. As you can see, this is pretty low. I mean, it's not like the numbers that we talked about in catalytic reforming, 2, 3, 4, 5, 6, or 7. It's pretty low, 0.06. Essentially, we don't actually recycle any hydrogen. It's only basically dissolved form of hydrogen. And it is basically three purposes for which we actually put hydrogen along with the feed. Number one, you must have guessed by now, is to actually saturate the benzene. Sufficient hydrogen for saturating the benzene, and also for ring opening of naphthalene into paraffins, and of course the rest of the hydrogen to be able to actually remove the coke deposit on the catalyst. So we don't actually then recover this unconverted hydrogen as such; it just goes into the fuel gas. So we don't invest on the compressor for recycling this hydrogen. So there are three very important purposes of putting hydrogen along with the feed. Uh, of course, I'll repeat, it's to convert benzene to cyclohexane, the cyclopentanes and cyclohexanes to corresponding paraffins. And number three is to keep the catalyst clean. As far as the pressure is concerned, I think you guys must have realized by now that since we are converting 1 mole of normal paraffin to 1 mole of isoparaffin, that means whether it is pentane or hexane, so normal pentane to isopentane and normal hexane to isohexane, there is no increase or decrease in volume. Okay, and so actually the reactor pressure doesn't have any influence as per the Chatterjee's principle. But we keep reasonably high pressure, 30 bar, at the second reactor outlet. So basically, the reaction takes place in a mixed phase. In other words, the light naphtha, which actually boils between IBP, initial boiling point to 90-95 degrees Celsius, is actually essentially in liquid phase, and you have dissolved hydrogen in it. So it is, partially vaporized, but mostly in liquid form. That is why it is called mixed phase. And so actually, the isomerization reaction, unlike catalytic reforming, in catalytic reforming, the whole reaction is in gas phase. So the entire feed is vaporized, and the whole reaction is in gas phase. While here, the pressure is kept high in order to actually, increase I mean, to suppress the vaporization of the light naphtha. And this is actually the reaction takes place in the liquid phase. We do have, of course, chloride injection continuously because the hydrocarbons they actually leach out the chlorine from the catalyst. There's a continuous loss of chlorine, so we have to inject chlorine continuously. So this is either carbon tetrachloride, or as I said before, when I was teaching you catalytic reforming, it is perchloroethylene. If you don't inject chlorine, the catalyst will die. I mean, because ultimately it will lose the chlorine and will get converted to just plain aluminum oxide, which doesn't have that level of acidity as the additional chlorine that you need to add. And talking about catalyst poisons, as usual, there are many poisons. Sulfur, of course, remains one of the prime poisons of this catalyst because of the platinum present on the catalyst. There's a danger to actually convert platinum to platinum sulfide and lose the platinum altogether. So actually, we limit the sulfur content to less than zero point 0.5 ppm, which is done in that naphtha hydrotreater which I talked to you about. The others, of course, have mild or simple. These are like heavy metals which have a long-term impact. So after 4 or 5 years, you might have to change the catalyst. But with the water, particularly if it is platinum and chlorinated alumina, is a major killer. It's a permanent poison. In fact, the free water is disastrous. So actually, what we need is after the naphtha hydrotreater, we need to actually put feed dryers so that we actually dry the feed. This, of course, we have actually discussed earlier as well in terms of how actually sulfur deactivates the platinum. Water actually very large dryers are put in. In fact, 1 kg of water destroys 100 kg of the isomerization catalyst. So we try to limit the dew point of the gas below minus 30, minus 40 degrees Celsius. And there are moisture analyzers which are actually, provided for the operator to check the moisture coming along with the feed. I think I'll skip some of this. So let's get on to the flow sheet. Uh, as I said before, one reactor is not shown here, which is the benzene reactor, because actually that reactor is required anyway to saturate the benzene. So what happens is that this is the flow sheet with chlorinated alumina. So you can see you got a dryer with the hydrogen coming in, and you got dryer on the light naphtha coming in. Both are mixed together, and they go through a typical feed effluent heat exchanger, as you would have guessed by now. That means the product coming out actually preheats the feed, and the rest of the heat you provide by MP steam, and then you inject the chloride, and then you go into the first reactor. This first reactor is operating at a higher temperature, and so you cool the reactor effluent coming out, and then you go into the second reactor and you cool this reactor effluent by preheating the feed. Okay, so this is some kind of energy conservation here, right here. And of course, the temperature levels are reasonably low in terms of 160, 170, maximum 180 degrees Celsius. That is the reactor inlet temperature. When you come out, you go to would be about 120 to 130 degrees range, and that goes into the second reactor where you take advantage of the thermodynamics. Now, after all this reaction, then you go into a distillation column. So if you remember, we talked about hydrocracking, etc. So you do get some light ends formation and some unreacted hydrogen. So you need to have a kind of a stabilizer or a stripper, if you might call it accordingly. So it's almost like 95% liquid, 96% liquid coming through. So what you do is that you strip out the non-condensables, like for example, the LPG and unconverted hydrogen out from the top. And this is where you get your isomerate, which has got 83 to 84 octane. This is what we call as a once-through isomerization. That means the feed comes in, goes through two reactor system, goes into the stabilizer, and then you get your product. That is the isomerate. There is another technology. There is another system which people implement, and this is something that you will see in almost all refineries. And this is not once through, but it is a recycle, and it's a very interesting concept which has actually helped us to get around this major limitation in isomerization, where actually you have to operate against a constraint of equilibrium control reaction. So what you do here is that you take the C5 C6 feed, uh, C5 C6 feed, and you actually mix that with the hydrogen. You go through the isomerization reaction, and then go through the you actually distill out the isomerate, because what you get out here is a mixture of isomers plus normal paraffins. The isoparaffins are having a lower boiling point as compared to the normal paraffins. So what we do is that we use a reasonably tall distillation column with almost like 80 or 90 trays, and we separate out all the isohexanes from the top. And so basically the IC5s and the IC6, etc., etc. And that is actually our product. And we take a side stream. The bottom, of course, is all C7, the heavies. So that actually also we mix along with the isomerate, because this is also having a pretty good octane. While actually the side stream is something which is like a normal hexane, unconverted normal hexane, etc. And single branched isohexanes, like 2-methyl pentane or 3-methyl pentane. So that actually we recycle back along with the feed. So what essentially we are trying to do is that we are actually taking off whatever is unconverted and sending it back along with the feed. How it helps is that for let's say 100 tons of isomerate that we are producing, it actually reduces the total amount of feed that we have to now put in because we are recycling part of the unconverted material. So there are three big advantages with this particular scheme. The first big advantage is that actually by recycling the unconverted material, we actually break the barrier of this equilibrium control reaction. In fact, it can even help you to use platinum on modernite as a catalyst here. So if I, instead of using chlorinated alumina, I can use platinum on modernite, operate at about 270 to 80 degrees Celsius, get all the advantages of no effect of water, etc., etc. So I don't have to invest on dryers. And in spite of the fact that I've got low conversion, I can actually recycle the unconverted material back and I can actually break that barrier. So that is one big advantage. The second advantage, of course, is that you get a higher octane of your isomerate because there is no unconverted material now present in your isomerate. If you compare that with this flow sheet, this isomerate contains all the unconverted material as well. So this octane would be lower as compared to this octane. So you can see that while this is 83 to 84, this is much higher, almost getting into the early 90s. And the third big advantage, of course, is that for the same octane barrels, you reduce the feed input because you recycle the unconverted material. So, but of course, nothing comes free in this world. You need to invest on the de-isoxyanizer column. But let me tell you, one of the companies here, I mean, we don't have to really talk in confidentiality here, but Bharat Petroleum here in Chembur, in Mumbai, did a very innovative idea. What they did was actually they put a divided wall column in the de-isoxyanizer. The de-isoxyanizer was a divided wall column where they actually could produce pure normal hexane as a side product. That means the product which was unconverted. And rather than recycling it back to the feed, they actually withdrew it as a product stream. So, in fact, this particular technology helped them to produce not only isomerate, but also to produce a very pure normal hexane, almost polymer grade normal hexane. And that actually helped the country to stop import or to reduce import of polymer grade normal hexane. And let me be, very frank with you that in Reliance, we actually started buying that normal hexane from BPCL rather than importing it in our polymerization plants. Large number of polymerization units, particularly slurry polymerization or solution polymerization, use normal hexane as a media. These are actually like to make LLDP, HDP type of polymers. So you need normal hexane, and which we need a very pure form, and they are able to produce it from here. So this is a big advantage that you get from this unit because there is no sulfur, no aromatics, and these are the two major specification on polymer grade hexane. What people have also done is that if you recall, I had mentioned that the feed contains isomers. Now, if the feed contains isomers, it will inhibit isomer formation. So, some technology suppliers have actually proposed to put a de-isopentanizer upfront. So, actually, you take in the feed, you remove all the isomers that you have, so that you make the feed rich in normal paraffins, which makes sense because actually when normal paraffins get converted to isoparaffins, if you already have isoparaffins in the feed, then you don't actually shift the equilibrium too much towards the right because it's the equilibrium control reaction. This helps actually to remove the isoparaffins upfront, but of course you need to invest on a tall column. And so the normal paraffins can then go to the isom and then the journey the same way. But you get actually yeah, a much higher conversion than in the isomerization unit. and you need less catalyst, and the cost of the isomerization reactors go down by putting the deisopentanizer upfront. But of course, it costs. These columns are tall. I mean, these are separating isoparaffins from normal paraffins. So the boiling point difference is hardly 7 to 8 degrees, which needs. So if you have a very low relative volatility of something like 1.04, 1.05, you need large number of theoretical stages. So actually, why we do all this is very nicely and very succinctly, covered in this graph. Effect of recycling unconverted normal paraffin. So if you plot research octane number at equilibrium, which is an equilibrium control reaction, versus temperature, I think the scale is hidden here, but it is the temperature. Yeah, you can see. Then what happens is that if you don't do any recycle, isomerization without recycle, we need to actually operate in this range in order to get reasonably high octane. So that's why you need chlorinated alumina, right? This is for a feed containing around 60% C5 paraffins, around 30% C6 paraffins, and 10% cyclic components like cyclopentane or methyl cyclopentane or cyclohexane. So here for this actually around this temperature like 100 to 150, 160, you need to operate at this stage. You cannot operate at these temperatures. Otherwise, you get a pretty low octane. But if you actually recycle, like for example, either in this scheme or in the scheme before, where if you recycle the unconverted paraffins, then actually you really don't make any impact on temperature because although by equilibrium you get lower conversion, but then you recycle the paraffins back. Of course, you need to invest on the pump as well as on the size of the reactors, etc., etc. But then the great advantage with this, the complete insensitivity overall. I'm talking about overall as you go out from the unit. So this is the research octane number of the isomerate coming out without recycle and with recycle. And you can see that it helps us to actually take advantage of using a more robust catalyst like platinum or modernite. And this is why actually the industry prefers. And as I mentioned to you, BPCL did a great job in making getting the idea of putting a divided wall column to be able to recover normal hexane. So that's all I had actually as far as the isomerization is concerned.